We've been looking at van der Poel's oscillator. We've looked at the case where mu was very large, where we could have the relaxation oscillators where all our dynamics was dependent on the null clines. And then we could basically find the null clines, and then the orbits crawled along the null clines, jumped to the next one, and then went up. And so we could almost find an analytic solution for the orbit, and we did use a very good approximation when we started looking for the period. So what we're going to do today is we're going to look at the other limit. So we're going to look at the limit when mu gets very, very small. So when mu gets very, very small, we don't stick to the null clines. We are rather much closer to an unstable spiral. So we're going to use a different set of analysis techniques for this case as what we did for the relaxation oscillations. And what I'm going to say is this set of analysis techniques is important. In fact, most of physics and most of analysis was based on this perturbation theory technique. In fact, before they had computers, this was the major approach to actually solving problems. And it's actually, I'm going to give you just a flavor of it. I'm not going to go as in depth as I think the course is done in the last. It's the one thing I've shortened, mainly because there's some sort of finicky things that I think once you know what it's about, if you ever need it, you can go and read it up. Okay. The chaos stuff was newer and it's less accessible, so that's why I decided to focus on that. But I do want to give you a flavor of it, and by no means it is important, so it's not unimportant, and it's very, very useful. But unless you're going to go in depth and solve a new problem, you are not going to need it as much. I actually use it in relativity quite a lot. Because you can't solve the equations analytically, and you can also not, in some cases, solve them numerically. So that's where I've used it. So I'm going to give you a flavor so you know where to start looking. You can know where the major problems are, and I'm going to basically solve Strogatz. The book they used, use Strogatz. The book that they used in the past, as I said, went more in depth, but we're not going to go that far with this thing. Okay, so let's just look at the van der Poel oscillator. There we have it from last time. Last time mu was large. And now we're going to look at the case where mu is much, much less than 0, or much, much less than 1. And so you can see it's basically a harmonic oscillator plus another part, right? A harmonic oscillator plus a small dangling part. So I'm going to do the same thing as what I did at the beginning of the last lecture, and I'm going to simply plot for you where the what the van der Poel oscillator does. And I'm going to start on the left-hand side with exactly the same picture as we had, all except I'm now going to decrease mu. Okay, so on the left-hand side, you have the transition from your relaxation oscillation that you could describe analytically to another type of oscillation that you can describe also analytically. But all these things on the left, you cannot actually apply any of these methods. Okay, so these things on the left lie between the two. And it's where the shape kind of changes from the one kind to the other one. So there you cannot apply it. There you have to either use your phase diagram, plot the null clines as we've done, but you can't actually use any one of these methods. So know there's a regime in which you can't, but know also that the one sort of description goes smoothly into the other one. Okay. So even though there's a point at which you can't exactly describe it using any one of these, the dynamics remains the same. There's a smooth transition. And that also can be seen in that Leonard system, because the van der Poel oscillator is a Leonard system, where they actually prove there exists a unique limit cycle always. And this is just another sort of realization of that. The unique limit cycle continues to exist. It changes its shape. Your analytic methods of describing it changes from the one extreme to the other one, but it's still there. So I'm just going to remind you how it changed. So this you've seen before, except now it's backwards. So it sort of goes from some funny duck shape to square to round. Okay, and when mu is equals to 1/5, this is where we start actually being able to apply the perturbation methods that I've mentioned now. Okay, so let's just see how it continues to change. As long as mu gets smaller, okay, so there we have again, so mu is 1/5, it's sort of semi-square, goes to 1/10, it gets rounder, goes to 1/0.005, the limit cycle actually gets bigger as mu gets smaller, right? So it's a very odd shape when mu is greater than 1 over 5, but now as you go into 0, it just gets more and more spherical, and it gets larger. Okay, so those are the things. So the pictures on the right, the approximation methods we're going to start introducing are very, very good. So that's where they're valid. So this class of systems on the right is basically known as weak oscillators, okay, or weakly nonlinear oscillators. It's basically an oscillator where you've tweaked it a little bit, right? Whether you're driving it or whether you're damping it, it behaves very, very close to a center, okay? Typically, these weakly nonlinear oscillators are perturbing off a center, and you see now exactly why. Okay, so the normal form that they have is basically this thing, which is a linear oscillator, a center. Note that you can put another constant in there to change the frequency, and you'll do that in one of the problems. So this analysis is basically with time rescaled that it is 1 over there, plus epsilon times some function of h and x dot, and so it's of position and speed, and you want to, and the h can be anything as long as it's smooth. Okay, so, and the main thing that we assume to actually make the analysis possible is that epsilon is small, okay, because if epsilon is small, then you kind of can do a series expansion and you can go on. So we have your linear oscillator is the blue part, and then the damping part, h, is basically assumed to be an arbitrary smooth function. Okay. So analysis technique we're going to do from now for the next 2 days maybe is going to be looking at those kind of functions. Okay. And the solution of that thing is always a slow winding kind of spiral. Okay. It very, very, very slowly winds. It increases. In certain cases, it decreases in certain cases depending on what h is, right? If h is just x dot, then it's just going to decrease to a fixed point. Okay, it's going to spiral into a fixed point. If h is more like the van der Pol oscillator over there, then it's always going to go to a limit cycle. So you only have 2 possibilities. And okay, so it asymptotes the limit cycle if it exists. Okay, so what we have is something that looks like this. So just to give you an example of it, so we have, I'm going to draw you the limit cycle once again for the van der Pol oscillator when mu equals to 0.2. So you can already see that I'm looking at the smallest one over here, right? Like mu is equals to 1 over 5. So there we have our limit cycle. And if I actually plot the trajectory, it's actually very, very, well, it takes a long time, right? So I'm going to plot the trajectory starting at some point, and I'm going to wait for 0.0, like a quarter of a second, and then I'm going to plot a bit of a trajectory, then I'm going to plot another bit of the trajectory, just to show you how slowly it actually spirals in, because this is in fact necessary to be able to do the analysis we're going to do now. Okay, so here is a trajectory that starts, I think, at like at -1 or 1, 0, and then it spirals in, so 0.02. So it spirals in really, really slowly. The trajectories are very, very close together, and that is necessary for the analysis we're going to do. Okay, we're going to make certain assumptions in actually trying to find an analytic solution here, and the assumption is it's got to spiral in slowly. And so if you get an answer and it doesn't, from your thing, you've made a mistake with your, well, you've either applied your perturbation theory where you can't, or you've made a mistake. Okay, so in the next quarter of a second, it does that. In the next quarter of a second, it does that. In the next final quarter of a second, it does that. And then I got tired, but it's very, very close to your limit cycle. Okay, so all the things in the system does that. So the next part is I want to start looking at the analysis technique. And the problem is, it's perturbation theory, so I'm going to give you the easiest one, but the problem is it fails, okay? And understanding why it fails is important, because it actually shaped the whole of the rest of the means of analysis. And but it does already give you the idea of what we do. So regular perturbation theory says, fine, we have a function that implicitly has epsilon in it, right? Epsilon changes, we can see from the previous things the size of the limit cycle changes, as well as the rate with which it spirals to the limit cycle. So we would like a perturbation theory that also, a solution that actually captures both things, as well as permits us to compute the period of how long it takes the orbit to go around the limit cycle, because that's the physical thing we are trying to calculate. So just the definition of perturbation theory to start is that we basically seek a solution where x is a function of t and epsilon, and we force it to have a certain form. And this is important because in later techniques we're going to force it to have a different form. So the assumption you make at your beginning of perturbation theory actually influences what you can do with it. So the first assumption is we say that it's x of t at 0, in other words, the solution when epsilon is 0, plus, and I'll prove that actually, plus epsilon x1 of t plus epsilon squared x2 of t. So it looks kind of like a Taylor series expansion, okay? But it's more than that, because the actual function you're putting in front is a function of t, okay? And what we do now is we basically make this assumption for the solution, and then we push it into the differential equation, we work out the consequences. And when we do that, we're going to get certain results out, and it's not going to be able to describe, actually this approximation is not able to describe the solutions exactly. But it still can tell you stuff about it. In fact, the most important thing it tells us is how to actually do it in a nice way. So let's go on. Okay, so I'm going to call that equation 1. The next thing is I'm actually going to apply it to an example. So in this case, there are usually three problems that are useful. Is that from a Paul's oscillator, there's a Duffing oscillator. But the problem I'm going to apply it to is actually a problem that I already know the answer to. Sure, be good. Okay, I'm going to apply it to the damped linear oscillator because we want a thing with an analytic answer. And for the damped linear oscillator, we've been studying linear systems, we have an analytic answer. And this is a very good approach if ever you do a perturbation expansion, right? And in fact, if ever you make a numerical scheme, always find something to which you have an exact answer to test whether your method works, okay? And it's necessary that it produces the exact answer rather than some rubbish before you go on, okay? There are a lot of physicists that have applied methods that are not convergent to series where they have not properly checked where it works, and engineers that did the same thing, and it fails spectacularly. Okay, so it's always wise an approach just to see whether your method works. I mean, as I said, it's basically this guess of an assumption that actually makes the whole thing go, right? So it's dependent on your guess. So choose something to actually check that the approximation works. And so it's basically that equation. You can see our h is simply 2x dot, but it's linear, so you can write it in first order form, work out the eigenvalues, and you'll find that it's a ellipse or a stable, or no, either a stable or an unstable spiral depending on the sign of epsilon. Okay, and then you can use that method that I derived a lot of lectures ago, where you can actually write down the explicit solution in terms of A. In other words, where you have x is equals to x cos t, or x0 cos t plus A over omega minus I over, I omega over 2 tau or something. Okay, so you can actually use that formula to write down the analytic solution, and I'm just going to give it to you, and then we're going to go on. Okay, so this is our sample problem, mainly because we know it. Okay. What you do also when you do perturbation theory, it's what they used to do before they plotted phase diagrams to the same extent. So you've got to specify your initial condition as well. So the initial condition is x of 0 is equals to 0, and just an easy one to choose a nice solution, x dot of 0 is equals to 1. Okay. And then your exact solution using the linear systems methods that we worked way back is that, okay? So, and you can see here's the trace is epsilon, okay, which is to be expected because you have epsilon there in the damping, and you have e to the minus epsilon t times 1 minus epsilon squared, 1 over the square root of this thing, times your sine term, okay? So because I chose x of 0 equals to 0 initially, it's basically the cos term vanishes and I'm left with the sine term over here, okay? So this is your exact solution as a function of epsilon, which is very, very nice because we can now apply and play with all our perturbation theory expansions and we can compare it, okay? Okay, so to do regular perturbation theory, in fact, to do almost any perturbation theory, what you do is you make this assumption, and you must note that it's a simplifying assumption, right? I've forced basically x to have a certain form, okay? Anyway, you make the assumption, and what usually happens once you force the function to have this form, if you put this function back into your problem you're trying to solve, you substitute it in, and then you group terms of epsilon, then you get a simpler set of equations that you can then solve one equation, get an answer, solve the next equation, get an answer. And this one is actually quite good for demonstrating that without making it exceedingly complicated. Okay, so you go about, you substitute equation 1 into equation 2, and what you get is this. It's basically ddt squared, so that's equation 2, times the solution you've assumed, okay? And the next term is just the constant term, so that's the x term, so it's just the solution you've assumed. And then the final term is basically 2 times epsilon times ddt of the solution you've plugged in. Now the trick is you collect all the terms of epsilon, right? Because you want your equation to solve the case, so you collect terms of even powers of epsilon. You want your solution to be valid for all epsilon. In other words, so look, if epsilon is equals to 0 in your equation there, you just have x dot dot plus x. And in this case, if epsilon is equals to 0, all your blue terms basically vanish, and you're left with x dot dot equals to 0. That's why I said this x0 basically is the solution to epsilon equals to 0. Okay, so you take that equation, you plug in your assumption, you write it out in painful detail, and then you start collecting all the terms of like order. Okay, so group terms together of like powers of epsilon, and what you get is epsilon dot dot plus x0 plus epsilon times x1 dot dot plus x1 plus 2 x0 dot, okay, is equals to 0. And then you go about and say, as I've just done, you want this to work for all epsilon that's small enough, okay? So because epsilon is basically a scalar, all the terms in front of the powers must be equals to 0. Okay, so, and then what you do is you take out, so you use your one original equation and you split it into several simpler equations. So at order 1, or you basically have this equation must be 0, and at order epsilon, you have that this equation must be 0. Okay, so those are the two things you now want to solve. The thing that you must look at is that, and this is true of all perturbation theory, not just regular perturbation theory, is the way you go about it is you solve for x0, which is the solution if epsilon is 0, then you have to put it into this equation. Okay, so you solve one problem, you get x0, then you put that one into the next problem, and then you solve it. Okay, so instead of having a complicated differential equation, you now have several linear differential equations with a source term in it. Okay, and you also have to do the same thing for the initial conditions, right? So now you have two different unknowns, x0 and x1. You have to specify initial conditions for both of them, and you use the same type of argument as what I've just used. So, for example, your initial conditions at t equals to 0 is x equals to 0 and x dot is equals to 1. Okay, if you now simply plug that into your assumption at the top, what it says about your expansion is that x0 of 0 plus epsilon x0, x1 of 0 plus blah 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 must be equals to 0, right? And the same argument holds, this must hold for all of epsilon, so we know that you can set x0 is equals to 0, x1 is equals to 0, sorry, x1 of 0 is equals to 0. So you have the t equals to 0 values for your expanding functions. Okay, the second initial condition on the x dot term is equals to 1. What you do is the same thing. You take this assumption up at the top, you take its dot, and then you set it equals to 1, and what you get is that x0, and then you do the same argument, look at the things of epsilon, and you have that x0 of 0 is equals to 1, okay, and x dot of 1, sorry, x1 dot of 0 is equals to 0. Okay, so you now have both the x and the x dot value of both of your equations that you're trying to solve over here. Okay, so the general solution for your first term is an easy one. It's just your sine and your cosine term, okay, because it's a harmonic oscillator, so you can write it down. So there is just, in fact, it's a special case of the more complicated things we've been solving. So you just have that x0 is a cos t plus b sine t. You go about choosing the constants in this case so that the initial conditions are satisfied. So because we have at times t equals to 0, the thing is equals to 0, so we have a equals to 0. At times t equals to 1, at times t equals to 0, x dot equals to 1. Okay, so we have b equals to 1. And we are done for, okay, so then we have the solution, x0 of t is just sine t to illustrate it. And the next one, and it's important, you have to solve these things in a hierarchy, whether you're using this perturbation theory, that's actually not going to work totally well, and I'll show you why, or whether you're using the next method we propose, you always solve order 0 first, order 1 the next time, and you keep going down. Okay, so now you have the solution, but the tricky part is you actually have to solve it so you can put it into the next one. You substitute it into epsilon, into the order epsilon, which is this equation, okay, and you now have to solve that thing. Okay, and this you can always solve, right? It's a driven differential equation with you need to find the particular solution. Okay, so you first, to solve this thing, you first find the base solution, which is basically this thing. Then you say, okay, my base solution, because I have to find a special solution on this side, is I just make a being a function of t and b being a function of t, and I put that assumption in here, and then I can solve for a and b as well. Okay, so you want to solve this with the initial condition of x1 of 0 and x1 dot of 0, and there's a problem, right? In this type of equation, it's a resonant forcing, right? Whenever you have a term that's being put in here on the right-hand side, that's a function of t, that has the same frequency as the natural frequency of your system, right? The frequency of this thing is t as well. Then what happens is the solutions tend to explode, okay? And we're going to look at more of examples of that later on. In the nonlinear case, it actually makes bridges collapse. But this is just an example that arises in the perturbation theory, and it's an artifact of the perturbation theory because we've made restrictive assumptions. Okay, but nonetheless, the moment you have such a term, you have resonant forcing, and even though you can write down the answer diverges, it explodes. And you can check, yeah, it usually means trouble. okay, because the solution grows exponentially, okay. And so we're going to just I'm going to write down the answer to this thing, and you can just check that it grows without bound, okay. So the solution to that thing is basically x1 of t is equals to minus t sine t. Now my first question is, did you solve questions like this in your second year course? Where you find the homogeneous solution and then you have to try and find the particular solution. You did, okay. So this thing you will know where, if you need to go and look for how I found the solution, you'll know where to look. Okay, good. So the very best you can do, the quickest you can do is basically you assume that and you say A and B are functions of t and you solve for A and B. Okay, so this is the solution we get, okay, and that's inconvenient, okay, because it gives us a result. It basically says that now if we go through the thing, formalism, we basically get that the prediction of regular perturbation theory is that x of t and epsilon is sine of t minus epsilon t sine of t. Okay, and we're just going to plot that, and we're going to have a look at it, because it actually is very, very important, because it explains why the thing fails. And then it more than explains why the thing fails, it gives us the clue of how to go about fixing it. Okay, so let's just plot this. Generally, when you get a function like this, the way I plot it is this thing, it's basically an envelope, so a function outside multiplying a carrier function. Okay, so sine oscillates between 0 and 1, and this function outside basically tells you how big those oscillations are. So when I get a function like this, I always plot this function and its negative on the axis first, and then I go about and I put the sine function in, just making its amplitude vary between the boundaries. Okay, so if I want to plot that thing, that's what that function looks like, and you can see that initially it converges, and then it gets to this point, and then it gets really, really large. And that's not consistent with the physics, okay. But it's an approximation method, so then you can say, okay, if I put in more terms of epsilon, it would look better and better. Yes, but eventually it's always going to diverge, this particular case, okay. But I just want to show you, for comparison's sake, what the real solution looks like, because it actually gives us the clue of what we're going to do next. Okay, so our exact solution that we found is this thing, which is basically a slowly decaying amplitude that's dependent on epsilon. Okay, and I think I plotted this for 0.2, so I plotted it for quite large epsilon. Okay, so it's a slowly decaying part, and there's the envelope. So this function, as a function of epsilon, looks like that. So you can see it's very close to our lines over here initially, but then it becomes markedly different. And then to plot the actual solution, I again multiply my amplitude, or my envelope, with a function. Okay, so I'm going to, and the analytic solution is a different frequency, a slightly changed frequency, if you solve it exactly, but it happens very rapidly. It happens very close to 1. So the frequency in the analytic solution is actually different from the frequency we got in perturbation theory. And if I actually plot it now, I can see what it looks like. Right, so there we go. It agrees very, very well, because it is an expansion. It was designed to agree, but it only agrees well for a short period of time. Okay, so regular perturbation theory, it's not as if we haven't done anything. We have found a method that gives us an approximation of the solution, but not for a very long time. It only works over here. Okay, and so after a certain amount of time, your solution is completely different from the actual solution. Okay, so it only works for small t, and it doesn't capture what happens for larger time. And the reason it doesn't capture it is that it doesn't capture the slow and the fast time scales that are available. Okay, So you can see, if we want to design a better method, there is a way to design a better method, is we must basically build in to our assumption that you've got one time scale that's basically slow, okay? In other words, you must permit this frequency in your approximation over here to shift, okay? And I'll show you next time of how to do that. And then you must have a different frequency, a different method that allows your amplitude actually to shift. So what this regular perturbation theory did do, it gave us an amplitude, but it gave us the wrong amplitude, okay? And it also gave us the wrong frequency. So if we can find a method that actually allows us to describe both, then we have a better method. And it's just more complicated to actually explain the mechanisms of doing it. And we'll start doing it the next time. So the other thing to notice over here is that your slowly decaying amplitude is actually, this term here is the inverse of your frequency shift. Okay, so they go different ways. And that's another thing that our assumption basically kicked out, that we couldn't describe this with our assumption. And the next method will actually find a way of building that in, where we'll actually say this problem has more than one time scale in it, and we systematically build up our perturbation theory that way. So I'm actually going to wait until next time before I start doing the full perturbation theory, because I want it in one class. What I am going to do is I'm going to tell you a little bit about where these things are used. Or not tell you a little bit, so perturbation theory is used a lot. It was used in GR, okay? And remember I said that it's important that you actually check it on a real answer. And this is why mathematicians have heart attacks as physicists, is that sometimes you can't. Sometimes in the history of physics, people have just used perturbation theory footy-foot, even though they knew it was non-convergent, okay? Because there was nothing else to do. So when they were looking at Einstein's equations, they had the field equations. They basically used this perturbation method to try and expand the equations, to try and actually capture those ellipses that turn like that. And they found, and they could prove that their expansions, they could actually do this with higher epsilon and just keep going, like we've done. And they actually showed that their term after the third post-Newtonian term, their term diverged. It literally became bigger than the previous two. Whereas here you could actually see that the terms get smaller and smaller, right? Your zeroth order approximation, if epsilon is 0, is just a flat curve. And if epsilon is bigger than 0, it sort of pinches it off. But what they actually showed is that their solutions exploded, but they used it nonetheless. And because there literally was no option. The other perturbation theory techniques either were too expensive, or in that you couldn't calculate them, or they didn't have them, right? Because the equations were so nasty. What they did finally, but they always kept this in the back of their head, and they sort of went further and further and further and further and further out on a limb to actually try and get answers, not knowing whether the answer is correct. Like, you had people developing PhDs that would mean calculating like the third term. Like one PhD would be like calculate the third term in one equation. And they would spend 3 years doing that. And in the end, they had absolutely no proof that their work was useful at all. And then only when people actually started solving the things on the computer could they actually see how tremendously accurate the things happened to be. So even they could formally show that their theory diverged as you added more terms. In the place where they were applying it, they were actually getting answers that were right. Okay, so in some sense, they vindicated their using of the perturbation theory by actually showing that it connected to the numerics. Okay, because in some cases, they knew it formally diverged, but they didn't know whether you were here, right? You could still have a diverging solution like this thing, which actually does diverge, but over here, if you only care about the answer for the first 5 seconds, then you've got a very good approximation of your thing. And that's actually what was happening in the relativity. Another comment is that these guys, we've done it in 2 dimensions. You can do the same thing in higher dimensions, okay? What it becomes tricky is when we had the one function going to the higher ones, you need to keep track of that, okay? You can always solve the solution, you can always solve the equations that you're given, that's the way it's been designed. But it's quite hard to keep track of all the things, the linear terms that come in. And when people do field theory with all these diagrams, I don't know if you've seen that. You know, like Feynman that does his field theory with all those diagrams in it. It's basically perturbation theory that he's used the pictures to organize how he does the calculations. So the calculations is always possible to solve, but organizing which ones to do when the system gets bigger becomes more and more complicated. So everybody's like Feynman, wow, he does all these things. It's basically perturbation theory in pictures. And very, very powerfully. And that history is also interesting. When they were designing it, what had happened is you had particle physics, you had experiments. They gave you results, nobody could explain them, and there were 2 people that were trying to explain them. The one was Feynman, and the other was Schwinger. Feynman was a very, brash guy. He would play the drums, he would do everything. And he got this method, and he had his diagrams, and people you can't prove anything. You're not a mathematician. What you're doing need not converge. He says, but it's giving me the right answers. Okay, so that made all the very rigorous theoretical physicists get old and grumpy. But what was true is they were giving him the right answers. There was another guy, Schwinger, who was a very, very focused, almost OCD type mathematician guy, who also looked at the same problem. He also came to the conference, gave a talk, doing formally this perturbation theory and doing it right. But it became so complicated because there were so many things coming in that people didn't follow him. And so you had the 2, so they didn't know that the 2 were actually the same. So you had the 2 camps. One guy was getting answers, the other guy was also getting answers. Feynman's method that he just somehow got was actually could answer more questions. The way he'd structured, because his pictures made it so easy to know how to calculate, people went further with that. Okay, so they could do more things. So popularity won out, people used Feynman, but Schwinger was there. He had this very rigorous method that he could prove everything. And it took 5 to 10 years. It took a real long time before a guy proved that the 2 methods were the same. Okay. And the moment they did that, you had both the power of Feynman's diagrams that could show you how to calculate, and you had the certainty that Schwinger had actually shown that his method formally converges, that it's a formal Hilbert space, that everything is mathematically fine. And you had the equivalence between the 2 which Dyson brought. All these things were tremendous feats in calculation. And all 3 people were actually necessary to make it work. And so all our calculations for particle theory and stuff are built on what those 3 people did. There's people that have tried to generalize it, but actually all the experiments that we explain is simply based on those things. What is also fascinating is that Feynman, that shows how you combine these things. He has all these pictures. People later mathematicians went and looked at the pictures. And there's a lot of really abstract mathematical theory that I don't know. I know how to use parts of it. I'm kind of but that actually is combinatorics of how these diagrams are fit together and what the possibilities are there and ways of counting. That actually becomes very important in doing more and more complicated calculations. Eventually, when they started writing computer programs to automate this type of thing, then the more abstract branches of mathematics also came in, and telling them, when they understood Feynman's diagrams better and better, and understood the group theory things underneath them, and that led to new results. So it's not one thing that leads to it. Several insights often come together to actually give this world something new. So most of our physics at the moment is based either on GR and on this particle theory that is basically perturbation theory with pictures with Feynman. The two are separate. They are not yet together. Nobody's managed to fit them together. That's the future. But at the moment, the two are basically based on that. And it took a number of people with different talents and different abilities to actually get it together in a good way. So that's all for me at the moment. Your homeworks are there. This one went quite well, except